This is a tuner I've had kicking around the loft for a while actually. Actually got so much stuff in the loft that I've actually lost track of what actually is up there. This is a Pioneer F757. This wasn't an entry level tuner, it's actually fairly high spec. Circa I think 91, 92 FM and AM, but it's got selectable aerial inputs as well, so you can actually have two different aerials, and that's useful if you're receiving long distance VHF signals from two different transmitters, which is quite often the case. You know, it's quite common that the BBC broadcast on one transmitter and all the independent channels would broadcast on another, and then you could just select the antenna you wanted for the appropriate signal. You know, if you're listening to Radio 3, or for example, you might want to select Rutum, and you just select the Rutum transmitter. And if you were, for example, you're listening to one of the independent channels, like for example from Beulah Hill in London, you just select the other antenna. Of course, yeah, most people don't have two antennas on the roof of VHF, but that option was always available. Has selectable IF bandwidth from wide and what they call super narrow. So narrow bandwidth on the IF allows you to filter out weak signals between sort of two strong signals. So if you've got a very weak signal that you're trying to tune into, and you're getting distortion from the other channel because it's an FM signal, there's a bit of deviation can bleed over to the other channels. That narrow bandwidth will allow you to resolve or help resolve the weak signal in the middle. It's also got high blend. They call it something different on here. I think they call it here, multiplexer noise reduction. Okay, so basically all that does is a high blend. Basically, I think all they do is they put a sort of like a high value capacitor between the two channels, and that basically acts as the higher frequency you go, the more blend towards mono it becomes, and that will actually act as a if you've got two frequencies in phase together, they actually null each other out, and that's actually basically how a high blend works, from what I understand of it anyway. So yeah, it's a fairly high spec tuner. It's typical of the sort of like the tuners of that era, the F91s and lots of the other models that are available, and it's in fairly nice condition. There's a bit of rubbing on some of the silk screen, but generally it's pretty good. I paid next to nothing for this. I just looked it up actually to see how much I paid for it. I paid very little for this tuner, and I wouldn't have done anyway because it wasn't a tuner I was particularly sought after. But what I want to do this evening is actually do an RF alignment or full alignment on it, and that's the process of this. The reason why I'm doing this video. So at the moment I'm set up to the tuner is set up to the Marconi signal generator. You can see here we've got our 75 to 50 ohm matching pad to match the tuner to the signal generator. We're looking at our levels here for DC levels, certainly on this Solartron 7150. Now the first couple of parts of this alignment are fairly straightforward, and it's to make sure that the voltage to frequency oscillator is working correctly. So basically, if I'm selecting 108 megahertz, the voltage is correct on the VCO to make sure it's actually tuned to 108 megahertz, because this is obviously like a digital to analog converter. So that'll be the first test. We'll set that up. I'm just going to go through a few checks just to see how it is. Now, I can't remember when I bought the tuner if I actually did any RF alignment on it at all, but I don't think I did, or if I did I might have done some very basic stuff. But it looks to me like that maybe it's got the classic example of what these tuners seem to have when they get a bit older. If you tune into a known good frequency on particularly on an analog tuner, you know, one with a center tuning frequency, and you tune into, say, I don't know, Radio 4, and you know it's tuned in perfectly on the signal strength meter, the tuning meter will actually show off to one side slightly. And likewise, if you tune to a channel where it's totally quiet, the tuning meter is always off to one side. That's usually a sign that it's an IF alignment error or discriminator error, usually discriminator. So I want to just whiz through this quickly just to see if this is working correctly or not. So let me try and zoom you in so you can see the meter a bit easier. There you can see the solitron there, and I think that should give you about the best view you're going to get with this setup. So the first test we do is we go to we don't put any RF signal in, so the signal generator is turned off, and it says 108 megahertz, which is showing on the display there. You might not be able to see that because as per normal it's reflecting. There you go, 108 megahertz. At test point 1 we should be seeing 21 volts. So let's go to test point 1. Oh, my lead's pulled out of the meter. That's a good start. You should be seeing 21 volts there. 21.03, and the limits are 21.1 plus or minus 100 millivolts. Okay, so we're well within 100 millivolts. We're at actually 30 millivolts. As 100 millivolts would be this point here. So that's working correctly. So that's the first tracking. It doesn't matter. It's specifying the IF bandwidth. It says that it doesn't matter which IF bandwidth you use. So the next check is to go to 87.5. So we just should go to up 87.5. And we're looking for 7.5 volts plus minus a half a volt. 7.5 volts. That's fine. So the VCO tracking's correct. For the next step is to put in a weak signal at 80 megahertz and adjust. What does it say? So it says adjust the maximum voltage between test point 10 and ground. So test point 10. So let's find test point 10. It's always a bit of an awkward spot to find these. I'm going to stick my boat race in the way to find it. Test point 7. So this is basically an RF gain check. I think this is basically we're looking at the meter output. Test point 9, test point 2. They're in any order, these things. They're just sort of like. Find test point 10. Got test point 11, test point 12, test point 3, test point 8, test point 9, test point 2, test point 5. There's one there that's not marked. Test point 7, is that? Okay, let me find test point 10 and we'll come back. Okay, we found test point 10. It's typical, it's never that straightforward to find. So we're on test point 10 now. Let's turn this around so you can see. So what it says is, I'm going to go back to the manual again. It says, so we want to put 90 megahertz in, and we want to put in a weak signal. So it's got 90 megahertz. So just adjusting the generator to 90 megahertz. Carrier frequency 90 meg. Tuning the receiver into 90 meg. It just said a weak signal. You should see it stop at 90 megs and the signal strength come up. There we go. It's fairly weak signal. Let's turn the RF level down. You should see the RF level drop off on the tuner. There we go. Let's go a bit further. Okay, it's a weak signal. It doesn't specify what level, it just says weak signal. And it says adjust the maximum voltage between test point 10 and ground. So we're going to adjust L1, T1 and T3. Now the L1, T2 and T3 are the RF front end coils. These 1, 2 and 3. So this is the matching, and the first stage is the preamplifier. So we're going to adjust those and then we'll see what we get. So we zoom in so you can see the meter a little bit. It's very important we use the correct tool. We use a plastic tool, and the chosen colour for tonight's tool is green, which is usually the standard one they use on all the Pioneer stuff. So let me try and get my hand under here without blocking the video. So this is the aerial matching one. This will probably have the least effect. But we're watching the meter for we want the maximum amount of gain. Now this is critical that you have the aerial matched correctly. If you haven't got the correct matching, then you're going to get the wrong figure. So let's try and get this right. Let's see it dropping off. We want this as high as possible. Okay, I'm getting some gain out of this. It's going back again. 2.55, 2.58, 2.63. Okay, 2.64, 2.66, 2.7, It's 2.67. There we go. We're about peak there. You can see it's not making any difference there. So that's good. That's the first transformer. The next transformer. Let's bring you down a bit so you can see the signal strength. Unfortunately, the depth of field of this camera is a bit limited, and you're not going to be able to see both at the same time. So this is the second transformer. We're going up at as high as possible. This core's a bit stiffer. Going the wrong way. Okay, this is coming up a bit. There we're back. We peaked. So it wasn't far off. 2.69. The final stage. So let's get that to 2.7. That'd be good. No, that's well peaked. So that's about the best you're going to get, 2.694. So that's the low frequency section of the RF amplifier. Now the next step will be usually to tune to 108 megahertz or something like that. Yes, 108 megahertz. So we tune to 108 megs. So we go back down on the tuner, 108 megahertz, and now we usually adjust the capacitor. No, that's normal on most radios. That all the low frequency stuff is done with the inductor, and the high frequency stuff is done with the tuning capacitor. So so at 108 megahertz we need to set our signal generator to put a carrier out of 108 megahertz. I'm not going to change the RF level. We can see here, can you see here, I can see here that the signal strength is about like it was at the lower frequency, and we can also see here that we've got 2.73 volts. And I'm going to do the 3 capacitors associated with that. Let me just stick my head in the way for a minute. So these are the 3 capacitors. So hopefully you'll see this on the meter. We're going for maximum voltage. Yeah, that one was well peaked, 2.75. Can't improve that one. First stage of the amplifier. .75. That's pretty spot on as well. The final stage. 2.76. So we've got tiny 2.75. Yep. So that's RF section is correct. Now what it says is go around a couple of times to check to get the maximum out of that. So what it suggests you could do is you go back to 90 megahertz and redo the cores again. I'm not going to do that simply because it's not necessary. That's only necessary usually if it's a mile out of adjustment. So what I'm going to do now is I'm going to move on to the next section, and the next section is the IF stage sensitivity and adjustment. And also I'm going to change the battery on the camera because the battery's just flashed up to say it's running out of battery. So next step with the IF. Okay, the next step, as I said, was the IF, and this is fairly straightforward. We tune the receiver to 98 megahertz, so it's 98.0, and it set our signal generator to 98 megahertz, which it is, and it says it's a weak signal, and the instructions are adjust T3 and 101 and 103 for the voltage between test point 10 and ground becomes maximum. Okay, so this sounds like a gain adjustment for peaking the IF, which is a slightly unusual way of doing it. But so we need to find test point 10. I think we're on test point 10, aren't we? Yeah, we're on test point 10 already because that was from the previous test. So just read this again, make sure I don't bug it. Yep, still on test point 10. So I'm going to adjust T3, 101 and 103. So I don't need to just check where they are on the layout. So it's just we can look now. 101, 103, where are we? Okay, where are we? So it's going to be 3 inductors that we check adjusting. 101 and 103 and 3. 101 and 103 and 3. Okay. 101, 103. 103 and 3. Can't see them at the moment. Leaping out at me. Right, let me pause this and find these inductors. Right, so we know now that we were in the right test points. Now we're adjusting this point here for 0, and this is basically our tuning meter, and this sets a discriminator as the centre of the bandpass. So it's right in the centre of the deviation, so you've got negative deviation and positive deviation. One deviation goes to lower frequency, the deviation goes to higher frequency. Now, we know the Marconi is set to the correct frequency, we know that's calibrated. We're tuned to 98 megahertz, and we're looking for 0 volts on the discriminator. And at the moment we've got 829 millivolts, so we want to get that down to as close to 0 as possible. And that would, if you had a center tuning meter, at the moment it would be showing one side to one side, it was off tune. So let's adjust that. Let's just adjust this core and try and find a place where I don't block the camera. Now you see, as I turn this, let's try and get you best view as possible. You won't see anything change on the display, but you will see that the meter come to 0 as I tune this core. So watch this. Not doing anything, is it? He says so confidently. Okay, so that's not making any difference, so I need to pause the video and find out what I'm doing wrong, if anything. Okay, the reason I was struggling too much was that we've got 2 test points very close together, and it's actually not very clear which one's which, and I was in the wrong test point. Okay, so we put a signal in. This is the discriminator adjustment, DC balance, and as I said before, shows you the tuning of the set basically. Let's give it a bit more signal. We're looking for minimum display on the multimeter here, so I'm just going to go up and adjust this core. Now you should this time be able to see the voltage drop back, or we want it as close to 0 as possible. See the meters come up on the tuner as well. I don't know if you can see that just popped up. So let's get as, when I say low as possible, close to 0 as possible. Obviously you can go negative. 0. That's pretty spot on. Okay, 37 millivolts. That's close to 0 as possible. Just going to turn the RF down just in case we're activating the AGC. You'll see this level drop off. We'll just check our level here. Stay the same. Just give it one more tweak just to make sure it's as good as we can get it. Now this is the adjustment that usually goes out on these tuners, and that affects the sound the most, affects distortion and things like that. So this is the yeah. So that's extremely touchy. Very good result from that. That will change as the set warms up or cools down. So that's that part of the bit that was actually probably most likely going to be the problem. So we'll move on to the next step, and the next step is monaural distortion adjustment. Okay, and I think this requires us to connect up to our audio analyzer. So we feed in a 98 megahertz signal, and we just test point same. Yeah, we're looking at the audio output, and T102A, which is the other side of that in transformer. Let me just show you the transformer. This is our discriminator transformer. This is the one we've just been adjusting to get the 0 volts between this test point here and the ground. Well, sorry, these 2 test points here and here. We've adjusted that for 0. Now the next one is the distortion. Now, funny enough, you can actually do this to a degree by ear, but let's do it with the audio analyzer. So we'll connect it up to my audio analyzer, and we'll have a look to see what we get. Alright, we connect up to the audio analyzer. We're basically doing the same thing, same level of RF adjustment. We're just adjusting the other core. We're looking for minimum distortion. It's at 0.5% at the moment, which most people wouldn't be able to hear anymore. Anyway, I've adjusted it by ear, and that's what sounded to me was about right. But what we're going to do now is adjust it again. So what's happening here is the audio analyzer is looking. It knows that the frequency incoming is 985 kilohertz. Oh, it's 985 hertz. But it also knows that there's a distortion in there of 0.5%. So we're going to adjust this secondary of this transformer, and we'll get that down as low as possible. So we're in the mono range. It's a mono signal being injected into the tuner. We'll adjust that so we can get that down as low as possible. This should be very twitchy. Okay, 3, 2, 3, 1, 3, 2. Yeah. See, that was done by ear, and that just goes to show you can actually. The human ear is very good at picking up distortion, and if you actually start adjusting things, you can hear that it's if it's distorted or not. So we got down to 0.5% on a fairly low signal. That's perfectly happy with that. So that's what does the spec say? It doesn't say. It just says for minimum distortion, I think. Or 0.3% or less. All right. Well, it's slightly high. Let's increase the RF level. See if this helps. Okay, it's full signal strength on the meter. We'll adjust it again. See if we can get it down any lower than that. So let's put some filtering on. 0.5%. And I've just selected some bandwidth limiting on here to 20 kilohertz, because you won't get anything more than 20 kilo. You won't get anything more than about 15 kilohertz for a tuner anyway. So we can get that down any lower. No, we're going the wrong way. It's pretty good. 0.5%. Quite happy with that. So that's that alignment done. Now, basically, that really sort of ends the end of the alignment. Really, the other ones adjustments we can adjust just to check and make sure the stereo decoder is correctly aligned is by fitting in a stereo signal. I'll do that quickly, and we'll see how that performs. Okay, the next adjustments I'm particularly interested to look at. This is VR203. Adjust that for minimum AC level on test point 3, and we've done that. That was spot on anyway. I'm not entirely sure what that's doing. It might be some sort of AM rejection or something. But we've done that. That's down to sort of like more or less 0 volts. So that's good. The next step is to check the VCO adjustment. Okay, switch to 108 megahertz. So let's put this back to 108 megahertz. Okay, tune to 108 megahertz. It says no signal going. No modulation. Let's just check this. Very clear. Modulation off. It says it should be a narrow or super narrow, wide or super narrow, normal or super narrow. So I'll keep it normal because it's the one I use mostly. Just VR601 and adjust output at test point 7, 38 kilohertz plus or minus 100 kilohertz. So this is a part. This is the tracking of the stereo decoder. So we'll connect this up to a signal a frequency counter, and we'll check our settings. Okay, we're fitting 108 megahertz in the signal generator, and we're expecting to see at that test point 38 kilohertz plus or minus 100 hertz. Ooh, I need to set the exposure right in this camera. God. And it's 38.0, so that's within spec, so that adjustment doesn't need adjusting. So we'll move on to the next step. Okay, the next step that we're supposed to do is step 10, and that's the pilot cancel adjustment. And basically that is like a filter to block the 19 kilohertz so it doesn't bleed out into the audio stage. I'm not too worried about adjusting that. It's not as critical as it used to be. I'll explain in a minute. That's adjustments that are unlikely to go out, and as I say, it's not that critical because mainly that was used for trapping the 19 kilohertz that used to cause interference with a lot of Dolby noise reduction systems on cassette. So if you're recording in Dolby, it could cause the Dolby to mistrack. Obviously most people don't use Dolby anymore, don't use cassettes anymore, so they're not using the noise reduction. So I'm not worried about that. I'm going to leave that adjustment alone. We're going to assume that that's never been tweaked and is good enough anyway. But the next step, 11 and 12, as you can see here, are a bit more complicated, and they are the stereo distortion and the separation adjustment. So stereo distortion adjustment on the super narrow range is you tune to 89.1 megahertz and you feed in a stereo signal with the left channel only through the Panasonic modulation generator, and adjust R505 and T101 to get less than 2% distortion. Now this starts to get a bit sort of like, well, you're sort of messing around with different adjustments, because it says if you can't get this adjustment right, go back to some of the IF and have a tweak with that. I don't think I'm going to bother with those two adjustments. The stereo sound isn't distorted, okay, I've done the stereo distortion. That was a real sort of very fine adjustment, and it didn't make an awful lot of difference. The rest is going to have to be handheld, I'm afraid. So this is a stereo separation adjustment. So what we're going to do is we're feeding in from the modulation meter. We're setting in a left signal only, and so we go to the right hand channel and we adjust the pot for minimum audio on the right hand channel. So we're listening to the right hand channel, we're actually only feeding into the left, so we need to adjust this pot. One of these pots, that one. There goes null. Okay, now I'm feeding into the right hand channel only, and you can hardly hear that. The volume's up quite loud. Just in the pot for minimum again. This is the other pot. Okay, stereo separation adjustment this is. Back to the left. Fine. So that's the stereo decoder adjusted. In theory, there are a few other adjustments that are really fiddly, and the distortion was one of them. This sets the distortion on the stereo decoder. Made very little difference on the distortion analyzer, and I was a lot of messing around. It made the video even more boring than it already is. But the alignment should be right on this tuner now, so I think we'll plug it back in and give it a listen, see what it sounds like. Okay, I completed the calibration on the Pioneer tuner, but I didn't actually do a video to demonstrate the audio, because the trouble is you can't use tuners to demonstrate how they perform, because any music you put on there, you get a copyright protection, copyright strike. It only takes 4 or 5 seconds of a bit of music and you've got a copyright. So I can't really demonstrate it anyway, because of obviously the microphones in this camera are pretty poor. The only way you're going to find out what a stereo tuner really sounds like is to actually listen to one. And that's really the end of the video. But I would like to state that FM tuners are still far superior to DAB. If you listen to a decent FM stereo tuner on a decent FM transmitter, for example Radio 3, I know most people don't, well, I shouldn't say most people don't listen to Radio 3, but a lot of people don't listen to Radio 3. You listen to Radio 3 on one of their live concerts and things, FM sounds absolutely amazing on a good tuner. It really does sound equally as good, if not better, than a CD. So that's one of the reasons why I like to keep these tuners going. I mean, I like all this old gear, as you know, anyway, but it's just something nice about an FM tuner. Sounds fantastic. You've got a good signal strength, and you haven't got any multipath distortion. An FM tuner sounds quite incredible. It really does if you've got a good tuner. And when I say good tuner, I'm talking about, yeah, that's 676 or 767, whatever it is that I've just done. The Pioneer F90, the Revox B160, the Quad FM4, lots of other tuners are around that are good. You know, it's the Roxanne sounds good, and even some of the cheaper tuners I bought. You know, some of the Sony ST370s that you can pick one up for sort of like 15-20 quid now on eBay. Sound amazing. Really do sound very good if you're into classical music. The problem is what's happening now is people are using and this has been going for a long time now, a lot of audio compression, because they're limited to the 75 kilohertz deviation maximum. Basically, they want their levels at 75 kilohertz deviation all the time. So if the music in a quiet passage, they still want to use almost all that 75 kilohertz up. Basically, it keeps down noise. That's the reason why. It keeps down. If you've got a weak stereo signal, you can mask that by putting a lot of audio into it, so you can't hear the hiss so much. But the problem is, it gives you no dynamic range. If you look at an audio waveform of a piece of music, for example, played on Radio 3, it's just like a flat all the way through. If you put it into a sound editing file, it's just flat. There's no peaks or troughs. It's just all the same. All the levels the same. You record that same piece of track or piece of music on from a DVD for a CD, and you'll see that how much compression has been applied to try and get the maximum out of the FM. Radio 3 don't do that. It's good. They do use compression. I can hear compression, but it's very subtle. And they're limited by their 75 kilohertz deviation. You can get into trouble if you exceed that deviation specified by the. I don't know who specifies it. It's whoever regulates the RF airways, I suppose. But I know some channels do slightly go over 75 kilohertz. I know that, for example, Capital Radio, transmitted from London, often go over 75 kilohertz. And on FM, that's not a good thing, especially if you've got a band close next door sort of thing. If you've got like something strong on 98 megahertz and you're listening on 98.5, you've got a lot of deviation from the 98 megahertz channel. You're going to hear it bleeding over if you've got a strong signal. So basically, yeah, I didn't do a demonstration on that tuner. It's a lovely sounding tuner. It's not quite as good as the F91, but it's still a very competent little tuner. And I hope you found it interesting doing the alignment. I really enjoy realigning these tuners and having a listen afterwards. They always seem to sound better than they do when you start off, but who knows? That's what I'm expecting. Anyway, that's the end of the video. Thanks for watching, and more to come.